All right, there we go. And so I will start by welcoming today's speaker. So we are delighted to have Professor Linda Valeri join us from the Biostatistics Department at the Columbia University Mailman School of Public Health. Dr. Valeri is an expert in causal inference with a focus on statistical and machine learning methods for causal mediation analysis, missing data, and sensitivity analyses for measurement error, selection bias, and unmeasured confounding bias. She is interested in translating statistical methods in public health to improve our understanding of mental health, environmental determinants of health, and health disparities. She's led the development of several commands for mediation analysis in SPSS, SAS, STATA, and R, and is currently funded by the National Institute of Mental Health to develop personalized causal inference approaches to investigate social and behavioral determinants of mental health that leverage data collected using smartphone and wearable devices. Moreover, she serves as an associate editor for the International Journal of Biostatistics, Biometrical Journal, and a statistical editor for JAMA Psychiatry and JAMA Network Open. And so with that, I'll turn it over to Linda. Take it away.
Thank you very much, Ravi, and everyone who's here today. So let me share my screen. Okay. Do you see the screen? Great. As Ravi said, please feel free to interrupt me during the talk. And today I'm going to present some of my recent work for causal inference methods in the context of health disparities research. I would like to start acknowledging my very precious collaborators with whom I started working on this project about 10 years ago, almost 10 years ago. When I was a postdoctoral fellow, I met Jarvis Chen, who is a social behavioral scientist, who introduced me to the issue of racial disparities in cancer outcomes. And through this journey with him and other faculty, my advisor at the time, Brent Kuhl, we started thinking about how we can address questions about determinants of disparities in cancer outcomes. And more recently, I've seen how methods for mediation analysis can be looked under the lens of health disparities research, but some work is needed to make them actionable for this particular field. And I will focus both on importance of interpretation of causal analysis in the context of health disparities research, as well as appropriate statistical methods that address the nature of the problem and the nature of the data. More recently, I started collaborating with a group in biostatistics at the University of Bordeaux. And it has been really fun to bring together these different groups of people to address these questions. So the premise of my work is that it's still an important problem across national institutes in our world to identify and eliminate disparities in cancer-related outcomes. We have multiple studies in both electronic medical record data or cohort studies that document such disparities across cancers and throughout the cancer continuum, that is from incidence to relapse of the disease, treatment, and mortality. However, there are still important gaps in identifying the different contributors to such disparities in the lifespan. What drew me as a statistician in investigating disparities in cancer outcomes is the complexity of such disparities that have multiple windows of time where they could occur in our lifetime. As I was saying, from the onset of the disease to when the symptoms emerge, when finally a clinical diagnosis is made and some treatment can be taken, and finally, hopefully for some people surviving such cancers, but some other unfortunately dying for those cancers or related complications of the disease. So as a statistician, I wanted to contribute formalizing relevant questions about mechanisms leading to potentially inequitable differences in cancer outcomes, as well as informing interventions to eliminate such disparities. And a key consideration that we have to make when investigating these questions is that cancer is a disease that progresses continuously over time, and for which decision in terms of screening, prevention, screening, and treatment happen continuously over time. In this talk, I will focus on a specific cancer, colorectal cancer, which is the third most common cancer in the United States, with more than 100,000 new patients diagnosed per year. And is also one of such cancer that is continuously demonstrating mortality disparities between two racial ethnic groups for which we have adequate data to study. Unfortunately, in my research in these years, I also confronted the challenge of not having enough data to really understand the interplay of both income and different racial ethnic backgrounds beyond African American and white Caucasian. And here, unfortunately, we will only focus on considering these two subgroups. However, some disparities are documented also for across the Hispanic, Latinos, as well as Asian groups, but we don't have in the data that I'm considering today, I won't have enough data to show these. From the American Cancer Society website, we see stated that African Americans have the highest colorectal cancer incidence and mortality rate of all racial ethnic groups in the United States. The reasons for this are not yet fully understood. I started this line of work formerly thinking about the contribution of delay in screening and therefore diagnosis of these treatments, of these cancers in the American population. And I'm now turning today in thinking about the role of timeliness of care once the cancer is diagnosed, where here I define timeliness of care as the rapid initiation of treatment after a definitive diagnosis, which is a key component of high quality of cancer treatment, but where we are observing inequities in the way care is actually delivered, and in particular in this aspect, how timely the care is delivered after the diagnosis. In fact, such differences in timeliness of care are documented both considering SEER Medicare cancer data sets as well as cohort studies. And again, particularly Black patients have been seen to receive treatments for colorectal, breast, prostate, and lung cancer in a delayed fashion with respect to white patients. So I would like today to present a novel methodology that I developed with my colleagues to investigate disparities in timeliness of cancer treatment as a potential determinant of disparities in survival for individuals who have been diagnosed with colorectal cancer. And in particular, we want to answer this question. If we were to intervene to eliminate differences in time to treatment distribution, such that more disadvantaged groups, in this case, the Black African Americans, were observed to be treated as timely as the more advantaged group, here would be the white patient population, how would we reduce disparities in survival outcomes? So you see that here we are using the word intervention, so this calls for causal inference methods. But these are interventions to change a disparity, that is, to change and observe the difference. Okay, so that's kind of the complexity of the causal interpretation of these effects, where we in practice want to intervene on one factor, that is, in this instance, timeliness of care, which happens to be intermediate between the exposure of interest, which is race, on which we don't want to intervene, and the final outcome, which is survival. So as our intervention involves an intermediate factor, this corresponds to a type of direct effect. Now, when I formalized this intervention, I said we would want to fix the time to treatment distribution rather than fixing, say, time to treatment to a specific level. So this is a type of direct effect for an intervention that is stochastic and is an intervention on a time to event factor, because our intermediate factor is waiting time for care for a certain treatment that is recommended given a certain diagnosis. So here is a already moving towards the end of the application. I'm showing you the curves for the waiting time, the waiting probability for these two racial ethnic groups, where we denote with the red or like pink line, the white, and the light blue for the blacks. We see that the blue line, the light blue line, is always on top of the red line, which indicates that blacks have longer waiting times to treatment than white. And our goal is to think about a new world, an hypothetical scenario, where we were able to shift the green line to match the red line. Here, these arrows that you see, these red arrows that want to push the green line into the red line. So such intervention would mimic a scenario where there are no disparities in waiting time for treatment between these two racial ethnic groups. So how do we think about addressing this causal question that involves a stochastic intervention on a time to event that is intermediate between an exposure and another time to event, which is a survival? We need to recognize first that this is a mediation problem, because the intermediate is a time, where we want to intervene is an intermediate factor. But also we need to recognize that is a semi-competing risk problem as well, because our final outcome, survival, is a terminal event, whereas the intermediate variable on which we want to intervene in distribution is non-terminal. So it could happen, for example, that some individuals don't survive to receive treatment. For those people, the timing of treatment is undefined, is not simply censored, as if, oh, study ended, so we cannot observe their outcome. In the causal inference literature, this is also called the phenomenon of truncation, okay? But in the statistical literature more broadly, is a semi-competing risk problem, because these two factors, survival and time to treatment, don't compete with the same strength. Survival is a stronger event than time to treatment, okay? So looking at the literature for semi-competing risks in mediation analysis, we really didn't find very much. In particular, we didn't find any application of in health disparities research that considered interventions on timeliness of care that accounted for potential problems of semi-competing risks. So we decided to think about new methodology to estimate causal effects to study the role of non-terminal intermediate time to events in explaining exposure effects on terminal time to events. In other words, methods for mediation analysis in the presence of semi-competing risks. So I introduce now more formally this problem and also some notation. R is our exposure variable, racial ethnic status, that is self-reported. X is a key factor, that is cancer stage at diagnosis, that we always need to take into account, because how do we define timeliness of care will depend on the type of diagnosis you receive. Because depending on, say, the stage at which you are diagnosed, your first, second, third lines of treatment are going to be different. So for example, in our application, we are going only to focus on stage 2 colon cancer patients for whom the first line of treatment is a surgery. And for other stages, actually, or other types of cancer, this clear definition of the treatment that they are recommended is not that clear. So we chose this stage and this subtype of cancer specifically for this reason. Now we denote with T waiting time to first line of treatment from diagnosis in months, which is a non-terminal event process. And we denote with S survival time, which is instead a terminal event process. And with K, we denote censoring time. YT and YS are the last observation times for the T and S processes, and delta T and delta S denote the event observation indicators. Finally, we consider C a vector of potential observed confounders of the time to treatment survival relationship. So we are going to have a vector, sorry, a matrix or a vector for each subject of observed data, which is the collection of all these variables that I just defined. And then we sit with our collaborators and think about what is the directed acyclic graph that could represent this study. And this is how we would consider this, this study. And there are other ways, more complex, where we could incorporate the time dimension. However, I don't want to go into that because it's not that, it could spur a lot of discussion, but just to say is non-trivial how you actually represent a DAG where your intermediate factor is actually a time to event in the presence of semi-competing risks, okay? But here we have our racial ethnic factor that we think is related with the stage at diagnosis, time to treatment, and survival time. And we think that there are baseline confounders that influence stage at diagnosis, time to treatment, and survival time. And for this specific work, since we wanted to have a clear definition of the time to treatment, we are considering the population of cancer patients that have a specific stage, okay? Now I introduce the notation for the counterfactuals. Now suppose that the terminal outcome of interest is survival time, and then the non-terminal mediator of interest is first line of treatment after being diagnosed. We denote with little g a fixed or stochastic intervention. And in this particular study, we are interested in a stochastic intervention that we call big G, which is a function of time to treatment at a certain X, which is at a certain stage and certain covariates for a certain racial ethnic group. So what is this big G? This intervention is a random draw from the time to treatment distribution observed for individuals with a certain racial ethnic group, certain stage, and certain baseline covariates. So when I said we want to understand what's the impact of shifting the time to treatment distribution in one subgroup of our population to what we observe in another one, we can reformulate this idea of shifting the distribution as, first, we need to learn what is the distribution of waiting time to surgery or treatment that we want to realize. Once we have that, the intervention is to drawing by chance for each people values for this waiting time for surgery from this distribution that we have learned from the data. Once this intervention is deployed, we would like to know what is the potential survival time under this new waiting time to surgery intervention.
Ask a quick question that appeared in the chat. So Lawrence Wu asks, are we assuming that all possible Cs are observed?
Yes, in this application, we assume that confounders are appropriately adjusted for. We can think about extensions to sensitivity analysis for unmeasured confounding, but so far, you know, in order to be able to identify, I'm gonna go to the identifiability assumption. If you wanna know what's the potential survival time after we intervene, shifting this waiting time distribution to little g, we need to know what are these confounders, these factors C that confound the waiting time to surgery survival distribution. So given this notation, I'd like now to define what are the parameters, the estimates that we care about. We first want to estimate, in the presence of semi-competing risk, the racial ethnic disparities in survival on the survival probability difference scale, which is also akin to a type of total effect. But again, I prefer to call it disparities because we don't seek any intervention on the racial ethnic group. So that's the difference in the probability of surviving after time little s, comparing the white group with the black group, where we denote also with R = 1, our black group, and with 0, our white. For a certain stochastic intervention little g, like the one I just defined, where we want to fix for everyone, the waiting time to treatment to be the one that is observed among the whites, we define here what I call a stochastic direct effect at time little s under intervention g as the change in the potential survival probability to be greater than little s between African Americans and white had we intervene, fixing in both groups the time to surgery or time to treatment distribution to little g. The next object that we might want to estimate is the proportion of the disparities that is gonna be eliminated by such intervention. Another causal contrast of interest that I call the stochastic indirect effect, or also stochastic distribution shift effect, is the change in the survival probability in one of the two groups. So in the, say, the African American group, when we change the waiting time for treatment in this group from what is observed in the population to this new hypothetical distribution that matches the distribution observed in the most advantaged group. By definition, the sum of the stochastic indirect effect and the stochastic direct effect is going to be equal to the disparity or total effect, which is a decomposition that is going to hold under weaker identifiability assumption, but also under weaker interpretations. In particular here, as I said, we don't want to seek any effect of race. We leave that as, we don't interpret that as a causal effect. So under which assumptions this decomposition holds and these stochastic direct and indirect effects are identified? First, under the consistency assumption, which is actually pretty tricky in this particular example, because saying I want African Americans to receive treatment as timely as white might not necessarily translate into the same exact treatment that they received earlier. There is a complexity into this quality of treatment. And therefore, it's not necessarily, it's possible that two individuals, they receive the treatment at the same time, but their potential outcome might be very different because the type of treatment they receive is different. So actually, I'm considering to extend this challenge of consistency and address it by including not only timing, but also quality of the treatment. And that's the direction that I'm taking. But so I would say this is not an innocuous assumption. Then we require the conditional exchangeability assumption, for which we can claim that we can establish a causal effect of time to treatment and survival, adjusting for racial ethnic status, baseline covariates, and in this case, within levels of stage. We assume that the positivity assumptions hold, and that we can also relax this, but for now we assume non-informative censoring. Under these assumptions, then the causal estimand for the stochastic direct effect and similarly for the stochastic indirect effect is identified with observed data. And we see here that the non-parametric estimator for this quantity is the integral over the time from 0 to S until we want to observe the survival probability, for the change in the survival probability between African Americans and white at each time point where people would be available to receive the treatment, standardized over this distribution of waiting time for treatment among the white group, okay? So our statistical problem now, after having thought about how we define these effects, we think that these effects, and I would like to discuss with you, are relevant in the context of health disparities research. The next step is how can we operationalize this non-parametric estimator and actually be able to obtain it and estimate it and having good properties for evaluation of uncertainty around the estimation of this quantity.
Looks like there's another question in the chat. I'll just read it out loud from Heather Gold. The question is, if timeliness of care for advantaged/white folks isn't the right timing, that is, that treatment should be sooner too, can this model account for that? And what about disadvantaged/Black folks who are getting timely care? We wouldn't want any intervention to change that end of the distribution. How is that managed here?
Thank you. So that's a very good question. That is, first look at your data. Whenever you think about a problem, look at what is the relevant intervention here. Here I'm considering a potential intervention G that could be relevant because here we see that at least on average, African Americans receive treatment later relative to white patients, okay? But as you observe, it could be that already the white group are receiving the treatment even delayed as well. And the other point you make is that this, of course, how these curves look is very different potentially across covariates. Okay, so we can modulate and incorporate all these observations when we define this G. That is, when we define this G, we are actually specifying that for each stage and covariates and racial ethnic group, we could define a specific distribution that we want to achieve. And it might be actually a distribution that is not even estimated from the observed data. It could be a synthetic distribution of an hypothetical world we would like to observe. So actually, this G could be really anything we want. But here, I wanted to kind of get at a little bit at the contribution to the survival disparity difference, the fact that whites receive on average treatment earlier than blacks. So what if we could eliminate such difference? Okay, but we could also have another question, which is, if we have in mind what would be the optimal waiting time for surgery, how can we improve the survival for everyone under that distribution? It's a different question, very important as well. Does this address the question? Okay, so I'll move on. Okay, now other notation, and here I really need the attention because we can kind of get lost here, because that's when it gets complicated, because we have two time to events, and these time to events can be sequential, one after the other, or one prevents the other to occur. Okay, so now I introduce this new notation that is called P subscript delta S delta T for a certain survival time given a certain racial ethnic group, which is the joint probability for survival and treatment status, so the joint probability of the mediator and the outcome, time to events, at a certain time, S, for a certain racial ethnic group. So now I can reformulate these non-parametric estimators for the disparity, that I also call total effect, and the stochastic direct effect as functions of this joint probability. Now, for example, the total effect or the disparity measure can be given by the difference between the joint probability of surviving not treated for blacks and surviving being treated for blacks minus the probability of surviving not being treated for whites and surviving being treated for whites. So you see this is a subscript. You see that at every time point, you can observe, is the person alive, yes or no? If it's alive, delta S takes value 0. If it's dead, then it takes value 1. But we are looking for the survival probability, right? So we are always interested in the person being still surviving. The second subscript is at each time we can see, is the person treated? Yes or no? Okay, and that's why when he's untreated, delta T is gonna take value 0, and when he's treated, delta T is gonna take value 1. Okay? So at each time point, if the person is still in the study, is gonna be surviving, so delta S is equal to 0, and is either gonna be treated or untreated. So we have to take into account this when thinking about the disparity measure. The stochastic direct effect is very similar to the total effect that I give here, except for the fact that now we want to learn what these joint probabilities might be under an intervention that changes the distribution of waiting time to treatment. That's why the only change is that we introduce this little g under these joint probabilities, okay? For the rest, everything stays the same, okay? So the kind of the core of what we did in this paper in terms of the formulation of a statistical model that wants to jointly account for confounding and semi-competing risks is to specify a semi-parametric model for these joint probabilities of being alive and treated or being alive and non-treated, okay? And we leverage the multi-state model framework to do that, so that we jointly model two survival times that are semi-competing. And we show how we can actually explicit these terms of joint probability as functions of cumulative incidences and hazards. So this formula, I don't expect you to understand what they mean. You can read the paper that is on arXiv to understand the proof that led to this solution. I just want to highlight two things. First is that here you see that this figure, this formula is either colored in green or in red. The parts that are colored in red are the parts that we can modulate with our intervention. So going back to the question I just addressed, let's say that you want to think about a particular intervention, an optimal waiting time for treatment that maybe is not even observed. Well, you need to modulate the hazard of transiting from being diagnosed, which we call stage 0, to the new stage of actually being treated. And this is what this 0-1 mean now. That is, the person over time can transit into different state. The first state, in order to be in the study, is that they have to be diagnosed. So, once they are diagnosed, they can transit to be treated.
Quick question from the chat. The question from Lawrence Wu again is, so is there where the exchangeability of TNS is important for identification?
That one, no, actually. What's relevant is to study the transition between being treated and survival. Because that's where, because our goal here is to study what's the causal effect of changing the waiting time to treatment on survival. That's the core there. That's the core of the causal inference machinery that we want to put in place. And that's why I'm claiming, and that's kind of challenging to understand, like in a 1-hour talk, that's a weaker interpretation of the mediation analysis. Because in the mediation analysis, we want to know what's the causal effect of the exposure on the mediator, what's the causal effect of the exposure on the outcome. But here, we don't want to intervene on the exposure. We only want to intervene on the mediator, which is a time to event, and we want to establish the causal effect of changing this distribution of time to treatment on the outcome. And is actually very difficult to adjust for this because there are so many confounders. So that was also a good question about what about these C's? Yeah, we will need to do sensitivity analysis for unmeasured confounding to kind of feel a little more solid in our causal interpretations. But maybe a figure that I have later on is going to help. So now, when I talk about these subscripts in that formula, represent this particular summary of what's happening in our study. Our patients enter in the study at stage 0 when they are diagnosed. And the dynamic that happens is that they either can transit into a new state that I call state 1 when they are treated, or they are not treated and they directly transit to the state of dying without being treated. Alternatively, when they are, after they are treated, they could die after receiving treatment. If the patient doesn't die, either receiving or not receiving treatment, they will be censored, okay? So if we go back to our formula, the first probability, that is the joint probability of being alive and untreated, will depend on the hazards of transiting from being alive, being diagnosed and treated, or the hazard of not receiving treatment, okay, and that is not being dead, okay. So the two transitions, this one and this one. And for the other objects of this formula, it's a little more complicated, but as you see, they are all functions of either the cumulative incidence, which is this, the cumulative hazards, this big lambda, or the hazards for each of these 3 transitions, from diagnosed to treated, from treated to potentially dying, or from diagnosed directly to the death state. So what is the interpretation of this estimator? Now, if we didn't want to give a causal interpretation to this statistical analysis, how can we at least interpret it statistically? So it would be the average difference in the global survival of Black patients when, or in the group of this Black patient that has a waiting time distribution as observed in the whites. Whereas if we wanted to give it a causal interpretation, it would be instead the average difference in the survival of a hypothetical population of Blacks where everyone has a waiting time distribution as observed among the whites who survived to receive treatment. So this is important when I say among white who survived to receive treatment, because there are other ways in causal inference that are being advocated to adjust for competing risks, which uses inverse probability of censoring weights, or in this case, truncation weights. So, and also this, maybe for some of you who are familiar with these techniques of adjusting for truncation, would be interesting to have a discussion. So in this method, we don't want to assume that we live in a world where no one dies, because we don't think that's realistic. Also because we are actually applying this method not only in health disparities research, but in other contexts where semi-competing risks are even much bigger, such as studies of dementia, where like actually majority of people die and the final outcome, let's say dementia, is not observed. And we don't want to think about causal estimates that create an hypothetical world where people never die. So that was the main, actually an important premise of using these different causal estimates and using a multi-state model framework that accommodates semi-competing risks. But it comes with other limitations. So we are not creating a population that doesn't die with this method. We are conditioning on the death rate that is observed in a certain group. So that's very important to keep in mind, because it means that these causal estimates are conditioned on a specific observed hazard of death that can be different in different populations, and therefore hurt the generalizability of the evidence. That is, whenever we report these findings, we have to be very good at also explaining what is the hazard of dying in this specific group of people. Because if we want to translate these causal findings in another population that has a different hazard of dying, these results might not apply to them. That's why also methods for transportability in causal inference would be super interesting, to extend these methods to. So again, in this interpretation, I wanted to highlight the distinction between these causal effects with the traditional causal effects in the presence of truncation that hypothesize that no one dies. Here, people can die, but we are conditioning on the specific time to death distribution. So how do we operationalize these estimators? So we actually have a command that is going to be available very soon in the CMA-verse R package for mediation that we have developed in my lab, so that we will be able to implement, we can be able to implement it very easily through that R package. But the idea of the algorithm is the following. You start by fitting a multi-state model for the transition hazards using the M-state R package, for example. And so here we are going to have a model that requires assumptions on how we relate the hazard of transitioning from diagnosis to treatment. What are the covariates that we think influence that? Then we want to study what are the covariates that are going to impact the hazard of transitioning directly from diagnosis to death. And finally, what is the hazard of, what are the covariates that impact the hazard of transiting from treatment to death? So once we have fitted this multi-state model, we, for each observed time in the range from 0 to little less, we predict the baseline hazards and cumulative hazards for each of these transitions under a new data for each racial ethnic group and time to treatment. And then basically this involves an integration process, a Monte Carlo integration. And finally, we estimate the causal effects of interest by plugging in these estimated hazards and cumulative hazards. And all this procedure is run within a bootstrapping for survival data so that we can evaluate uncertainty around these estimates. So we evaluated, are there questions? Okay. So we evaluated the performance of this approach with two alternative strategies that we saw are very common in epidemiology. So we didn't compare it with the inverse probability of censoring weights applied to the truncation problem or semi-competing risk problem because they answer different causal questions. So it would be interesting to write a paper about the implication of different definitions of causal effects within semi-competing risk problems. But right now we just wanted to evaluate, we can either ignore the problem of semi-competing risks or use this approach to go after the same causal effects. What is going to be the difference? And we consider scenarios where we either have a small problem of truncation or semi-competing risk, only 10%, which mimics what happens in our real data, or a larger problem of 40%, which is very likely in settings of transplant research, for example, or dementia research, where I'm using these approaches as well. We consider the setting of non-linearities, such as when we think that race and time to treatment interact in their effect on survival, which is very likely, and also accounting for the fact that maybe the effect of waiting time to treatment is non-linear. And we focus on evaluating, in this presentation, I focus on interpreting the stochastic direct and indirect effects. So we compare the proposed multi-state approach, an approach that excludes subjects who die from the data, and another approach that censors observation. So runs separate models for the survival time and the waiting time for treatment, which is very common in mediation analysis. You have two models separately for mediator and for outcome. And for the person who dies and their waiting time for treatment is not observed, it's simply coded as a censoring event. So on the left side, we have the difference in survival probability estimated by the methods compared with the true effect, where the true effect is a dashed line, bolded, and we see that is matched perfectly, almost perfectly, by our approach, whereas the other approaches that either exclude individuals who die from the analysis before receiving treatment. Sorry, I should have said exclude individuals who die before receiving treatment, or censor them. They are very far from the truth. And this is reflected on the right side, where we show the bias, which, it again is not, the effects are not very big in the first place. So actually I should have shown the relative bias, because the relative bias is non-negligible. Already the effects are kind of small. Again, because we wanted to mimic our study. And we see that they have inappropriate coverage and larger mean squared error. When the problem of semi-competing risks is more important, of course, these biases increase and the coverage can even go towards 0 for these, if we ignore the semi-competing risk problem. Any questions before I move on to the application? Okay, so we apply these approaches in this cohort study that is multi-center, is the Cancer Care Outcome Research and Surveillance Consortium that was established actually to determine how patients across different racial ethnic groups were perceiving the quality of their care in their medical centers. And the strength of this cohort study is that they chose geographical areas to mimic the SEER cancer registry. They collected a wealth of information about comorbidities together with cancer information, as well as patients' preferences regarding care and their satisfaction with care. So this is a really good data set, at least in the face page, to address this type of question. For us, it was very important to have information on self-reported health status as an important confounder, socioeconomic status, as well as information about their treatment regime, either self-reported or from medical records. And our analysis included 1,613 non-Hispanic white and non-Hispanic black diagnosed with colorectal cancer as first histologically confirmed diagnosis. So the first realization when looking at this data is that this patient population, yes, was treated in medical centers located in regions that matched the SEER study, but they were the premier medical centers in those areas. That means that we were potentially across the board underestimating racial disparities in survival, and we found actually important heterogeneities. And here we report the results that we found for one subgroup of patients, which was, as I said, stage 2, middle income, and diagnosed with colon cancer, so with this subtype. By the way we investigated these interactions were pre-specified based on prior work, where we introduced immediately, without doing forward or backward selection, but informed by previous work, interactions between race and age, race and gender, race and income, because those were found in previous work. So we see a significant racial disparities in survival for this subset of patients. And what I showed you before, for this same subgroup, a statistically significant difference in waiting time for surgery, which is the first line of treatment for stage 2 colon patient. And a small, but still present issue of semi-competing risk, where 70% of these stage 2 cancer patients died before receiving treatment. Such percentage was much higher in patients with stage 4, as we are not surprised. But in this group, also because of the aggressiveness of the tumor, there was not enough time to actually experience these delays in care. So again, every application is different. However, we showed that even with small semi-competing risks problems, there could be bias in traditional methods, and in fact, we see differences. So this is the main result from our work in the application of this method, where in the bolded lines, we denote the effects estimated with our approach, the multi-state model, and with the gray lines, the methods that ignore semi-competing risks, either using censoring or excluding subjects. So first observation, the black solid line which indicates racial disparities in survival, is the lowest, which indicates that there is a significant, potentially significant difference in survival probability. And later I will interpret, say, what happens, the 5-year survival probability, okay? The dashed line indicates the hypothetical difference between black and whites had we eliminated in distribution differences in waiting time for surgery. And we see that this line goes up, which means the reduction in this disparity. Okay. The other two methods show, first of all, lower disparities, and they also show no difference before and after an intervention. So now if we focus on looking at the specific time point, little s equals 60, 5-year survival probability difference. What we see with the multi-state model is that there is a significant difference in survival probability of 0.29 points, which is non-negligible, clinically relevant, given that the probability scale is from 0 to 1. This is a non-negligible difference in survival probability between African American and whites, which would be only slightly reduced to minus 0.26 if the waiting time to surgery difference between African Americans and white was eliminated, which reflects about an 8% reduction in this disparity. When instead we either exclude the subjects who die before receiving treatment, or we treat the models separately. So we model separately survival time and waiting time to surgery, and we treat the individuals who die before receiving treatment as censored. We actually don't observe anymore, don't estimate any more significant disparities, and no difference before and after the intervention, hypothetical intervention on waiting time for surgery.
And just one quick comment. We're just about out of time, so folks might start dropping off. Yeah,
I totally understand. I actually wrapping up. So we proposed estimates and semi-parametric estimators to evaluate the impact of stochastic intervention on intermediate censored and truncated time to event variable. The estimation strategy leverages the multi-state model that jointly models the semi-competing events rather than modeling them separately, which avoids issues of modeling compatibility, which are very often present in mediation. And we have applied this approach to evaluate the role of timeliness of care as determinant of racial ethnic disparities in cancer survival. Under stronger identifiability assumption, this approach can be extended to natural effects, but in that case, we will have to adjust for confounding in a more complex fashion. So another paper is really needed for that. And I thank you for your attention, and happy to take any other question.
So thank you so much. I'm going to clap on behalf of everybody. And so, like I mentioned, folks might have to drop off, but we can stick around for, a couple of minutes to take, one or two questions. So, if anybody wants to just unmute themselves and ask a question, then that would be great. Looks like some folks have to run, but anything?
Yeah, I'll ask a question. Hi, Linda. Great talk. So I have a question about the very last thing you said about extending results to kind of natural direct and indirect effects. So that, and with time varying mediators and or exposures, the big challenge in mediation is recanting witnesses, right? The time varying confounding. And so in this case, is there any assumption about, no recanting witnesses kind of implicit in your identification, or are you getting around that with the stochastic intervention?
Exactly.
Okay.
Exactly.
So do you have hope for Do you have hope that we can actually identify natural direct and indirect effects?
No, I think we can only go after randomized interventional analogs, because there are so many. This is specific to this application, I'm claiming, because there's so many factors that race will influence, and like lifestyle factors that then in turn influence health status, which then, and yeah, I have little hope for natural effects in the context of health disparities research. Maybe in other contexts, maybe more likely, but I cannot. I don't have right now an application where we could actually use the natural effect interpretation. Thank you for your question. Yeah. And again, I don't know whether we would want to find one where it's actually really important to get at natural effects necessarily. And but yeah, maybe people don't know about randomized intervention analogs to these effects, but basically the idea is that we do not claim that we are fixing we are gonna again use this idea of a stochastic intervention on the mediator, rather than thinking, oh, for everyone we will give them their own time to surgery if they were white or if they were black. It doesn't really make much sense here. It might make sense in other contexts, but at least not in health disparities research.
All right. Well, thank you so much. I think in the interest of time, we'll probably wrap up here, but I'll just clap once again. Thanks so much for that great and interesting talk.
Thank you.
And have a great day.
Thanks. You too. Have a good day.
All right. Bye, everybody.
Bye-bye.